We'll continue with properties of measures of information that we saw last week. And the first property we will look at is Fanos inequality. As I have mentioned before, this is one of the most important inequality that information theory offers. And it has many applications in statistics and communication and perhaps in many other areas. Okay. Essentially, what Fanos inequality gives us is a lower bound for probability of error for an Emery hypothesis testing problem. So here is one version of the inequality. I'll give you two versions. Okay. So this version says, okay. So this first version says, suppose you have a random variable x and another random variable y, so x and y, and their joint distribution, let's say, is pxy. Further, we assume x is uniform. So x is uniform on m value. So it's uniform on this set, let's say 1 to m. 1, 2, 3, 4, m. M is some number. Okay. Then what you can show is that if you use a function g, which looks at y, so this random variable y takes value in this calligraphic set y, and output x, and this can be even a randomized function. Can be randomized. Okay. So what is a randomized function? It need not just use y as input. It can use y and some independent coin flip. So it can be a randomized function like that. So then for any g, okay. So then, sorry, let me write it carefully. Then for any function g, we have the bound. What is the bound? Probability that x is not equal to g of y. So this is the probability of error. You made a function g to try to guess the value of x by looking at y, and you can even allow randomized function. And the claim is that this probability of error here is at least something, at least 1 minus, and this is the lower bound which Fanos inequality gives you. 1 minus the mutual information between x and y plus 1 by log of number of hypotheses. Okay, that's Fanos inequality. So this is very interesting. It's not, what it says is, it's not that you can make the probability of error as small as you want. How small you can make it depends on the number of hypotheses you want to resolve. So if you want to make probability of error, let's say, smaller than 1/3, then that puts a limit on the number of hypotheses you can resolve. It's roughly ixy. So you can roughly resolve as many hypotheses as 2 to the power ixy. This is log of the number of hypotheses here. Alright, so this brings out a very interesting interpretation of mutual information. It controls a number of hypotheses that you can resolve with a given probability of error. That's what Fanos inequality tells us. Okay, that's this first version. So how do we prove this? So let me give a slightly different proof from what is available in most textbooks. So the reason you can resolve these m hypotheses using about x using value y is because x and y are correlated. In fact, if x was independent of y, what is the best probability of error you can get? Can you think about it? You can take a pause and think about it. Okay, so now that you have thought about it, I hope all of you are convinced that you cannot do anything better than randomly guessing the value of x if x and y are independent. So for independent x and y, the best probability of error is as good as a random guess. In fact, the best probability of correctly guessing x is just 1 by m. Alright, so let me start with that observation. If x and y are independent, which they are not, this is a joint distribution here, but if they are independent, that means that is under the joint distribution px py. This is the independent distribution. What do we have under this distribution? The probability. So I'll put this as subscript here, px py, just so that we remember this is not under the actual xy distribution. Probability that x equals to gy, you correctly guess x from any g, is equal to, I'll give this proof for a deterministic mapping G. It's easy to extend it to a randomized mapping. So randomized mapping, this is a side remark here. A randomized mapping can be thought of as G of y comma u, where u is independent of x and y, and you can even assume it's uniform actually. So basically this u is used to select a mapping, and then you take the function of y with respect to that mapping. But you can extend this proof to randomized mapping as well. I'll give it for deterministic mappings. All right. So what's the probability of guessing x from y if x and y are independent? Well, that probability is probability that you see some y, and then x. This is probability of correctness. The value of x that occurs is exactly g of y. Okay, this is the probability of correctness. All right. But since x is uniform, this guy here, what's the value of this guy for any gy? This guy here is just 1 by n. Okay, and therefore this sum here, this particular sum here, okay, this sum just becomes 1. So if x and y are independent, which is that's why we were able to split it this way, this probability of correctness is exactly 1 by m, no matter what g you use. And this is very believable because x and y were independent. Okay, so the main idea behind a proof is that if x and y are independent, then your probability of error, so let me write that, px, so this implies under px py, the probability of error, so what is probability of error, x naught equal to gy, is exactly equal to 1 minus 1 by m. Okay, that's what this implies. So the main idea behind a proof of Fanos inequality is that if the probability of error is 1 minus 1 by m under independent distribution, how much better can it be under joint distribution, under original joint distribution? And the answer is that it cannot be too much better. Okay, the answer is that how much better this can be depends on mutual information. So how do we show this? Well, we'll use the data processing inequality. So formally, let me make some space for myself. Okay. So now we consider this channel, consider a channel. So I'll define a channel so that I can apply data processing inequality. This is a very heuristic proof. You have to read it slowly and think about it. I'll provide you notes, typed notes on this. Consider this channel W, which looks at x and y and outputs 0 or 1. This 0 or 1 indicates if error occurs or not. 1 is correct output and 0 is error. Given y, so what is my channel W? W I'll associate with this mapping G of 1 given xy is equal to the indicator function. So indicator function of x equal to gy. So when this event occurs, this function has value 1. When this doesn't occur, this function has value 0. That's what's an indicator function. And therefore, this probability is 1 if x equal to gy, 0 otherwise. That's the channel we have to keep in mind. So for this channel, we can use data processing inequality for KL divergence using the data processing inequality for KL divergence. Okay. The divergence between W of P, Pxy, or original distribution, the joint distribution, and the useless independent distribution, Px, Py. This divergence by data processing inequality is less than equal to the divergence between Pxy. Okay, so by the data processing inequality, we have a handle on how large this divergence is. But now let's examine each of these quantities here. So what is this first quantity? Let's look at this first quantity. This first quantity here. Okay. This is a binary distribution because W output alphabet of W is just of size 2. So what is W Pxy of 1? This is exactly the probability under Pxy of x being equal to gy. Okay, this is the probability of 1 minus the probability of error that we are interested in. So we will just denote it by p. We are interested in 1 minus p, remember? Okay. The other quantity that we see here in this divergence is this w of px py of 1. This is again the same probability of correctness, but under the independent distribution. This is under px py, and this is q. Sorry, probability of correctness, not error, correctness, and this is q. Okay. So then we can expand this divergence here as, and this guy is less than mutual information, remember, but let's expand it. This guy is equal to p log 1 by p log p by q plus 1 minus p log 1 minus p by 1 minus q. So what is p log? So we'll take out the numerator part first. So what you are left with is p log 1 by q plus 1 minus p log 1 by 1 minus q minus h of p. Okay. In fact, we already saw that under this useless distribution, this independent distribution, this q is just 1 by m, the probability of correctly guessing. So we'll substitute that value now. So this is equal to p log, we'll substitute it here, 1 by m, that's m, plus 1 minus p log m by m minus 1 and minus hp. Let's collect the terms with 1 minus p. So this is 1 minus p, that's the probability of error. You can view this as 1 minus p. So 1 minus p log right plus log m minus hp. You can check this is this is equal to this. Okay, and this whole thing is less than equal to mutual information. That's what we have seen. So this implies that 1 minus p is greater than equal to, did I miss something? So what I did here was 1 minus p, that's log m minus 1 minus p log m. So you have this, so you have log m here, right? So you get, yeah, right, so you take 1 minus p on this guy on this side, and yeah, this is correct. So you get log m minus the mutual information between xy plus hp, this is, and whole divided by the coefficient of this guy, that's log m minus 1 divided by log m minus 1. All right, so this guy here is greater than 1, log m by log m minus 1, and this hp is less than 1. This is the binary entropy of p. I didn't say that earlier. So this hp here is the binary entropy of p. Right. hp, just to remind you, is p log 1 by p plus 1 minus p log 1 minus p. So it's the binary entropy for this coin with probability of heads p. And as you know, binary entropy is less than equal to log of cardinality of the input alphabet here, which not this x, log of cardinality of the number of values which you are taking here. So p takes only 2 values, so this is less than equal to log of 2, that's 1. So this is less than 1. So I can just put 1 as an upper bound for it, and I can divide by a larger quantity. It will only decrease. It will decrease the numerator or denominator, therefore it will increase this guy, so you are subtracting more. So it's just weakening the bound. Okay, that's the form that we stated. So the proof you conclude the proof by noting what is this 1 minus p. So we had defined p as the probability of correct guess. So 1 minus p is the probability of wrong guess, probability that x is not equal to j. Okay, so that's the proof. Okay, let me just close this proof here. So this is actually a very heuristically appealing proof, somewhat magical but heuristically appealing. So what is this proof saying? This proof is saying that, see, if the distribution was independent, then the best probability of a correct guess that you have is 1 by m. And now the distribution is dependent. But although it is not this px py but this pxy, the distribution, but still you cannot improve this output too much because of data processing inequality. The best you can improve this by, the best distance you have here, that the farthest apart they are, is mutual information. And the fact that this implies some bound on probability of error is actually a very nice observation. It goes back to Harutunian, I think. Marton also used it quite a bit in deriving lower bound for error exponents, and you can find this in different places. But I think this proof is more recent. Anyway, but I hope you understand this proof. Okay, so very nice. So we have our first bound, lower bound. In fact, what we have derived is a stronger inequality. We only weakened it. So I'll just point out that actually you had an HP here and you had this m minus 1 here and something more than 1. But these small improvements are not what will help you typically in Fanos inequality. Fanos inequality is not tight in this constant typically. Okay, in the sense that it's okay to be loose here, and I'll just ignore this few, just be loose here, replace HP with 1 and all that, and you don't lose much by that. Alright, so this is some inequality that you absolutely have to remember. I will also prove another version of this inequality. Okay. I'll just first state another version here. Okay, so this is again Fanos inequality, but this is version 2. Essentially, I'll give a different proof when I'm proving version 2. So what this version doesn't, the second version doesn't require x to be uniform. Okay, so x. So the setup is the same as the first version. Setup same as version 1, but x need not be uniform. And what this version now says is that the probability, actually I'll not put it about probability of error. This version, it's better to state it in terms of conditional entropy. So this says that the conditional entropy of x given y is less than equal to probability that x is not equal to gy, log of number of values that x takes minus 1 plus the binary entropy of this probability. Okay, this is version 2. It looks very much like version 1. In fact, if x is uniform, I didn't follow my color theme. Okay, so let me put a red color here. Right, so this is the second version. In fact, if x is uniform, on 1 to m, then this hxy is hx minus the mutual information. So in this case, hx given y is equal to hx minus the mutual information, which is equal to log m minus the mutual information. And then you can rearrange terms here and get the same version. So this implies version 1. Okay, so this is another version where the upper bound is on conditional entropy, and it says that conditional entropy cannot be too large if the probability of error is small. So basically, if the probability of error is small, then x doesn't have much randomness given y. This is a slightly different interpretation. The first interpretation I think is more relevant for statistics. The second interpretation is used for showing what are called coding theorems, which we'll spend a lot of time on in later part of the course, right? So this second version now, let me try to give a different proof for it. This proof is quite brilliant actually, but it's in my opinion, it's slightly more opaque than this one, but definitely a brilliant proof. So how does this proof go? How does this proof go? It's a more standard proof. You can find it, for instance, in the Cover-Thomas book. So what does this proof say? It says that let me define this new random variable e. This is this indicator function. This indicator function, which shows up here also. So these two proofs are actually quite related, but completely nailing down their relation is perhaps a bit complicated. So this is the error event. Okay, probably this is the event that x is not equal to gy. One indicator of that. So this random variable e takes value 0 and 1. Now, if you look at h of xy, okay, maybe we should just look at h of x given y. That's also fine. X given y. This is equal to h of x comma e given y plus h of e given xy. But e is a function of x and y, and therefore once you know xy, you know e does error occur or not. So this guy here is just 0. So h of x given y is just this. Okay, so we'll expand this. So this is equal to h of, we'll expand it in a different order, h of e given y plus h of x given ey. Now h of e given y is less than equal to h of e because conditioning reduces entropy. So the first term here is less than equal to h of e. Okay, and the second term here again, because conditioning reduces entropy, different color, should use a different color. Yeah, one advantage of doing these lectures online is I can use many more colors than what I'm able to use on a blackboard. So I should use this privilege quite a bit. So this is h of x given y. Sorry, what have I done? H of e. No, that's not what I want to do here. Okay, this term I'll come back to. I'll retain this term for now. H of x given ey. Okay, let me retain this term. Okay, this first term here is exactly equal to h of p, probability of error, h of probability that x is not equal to gy. Okay, and it's the second term that we'll focus on now. So let's work out the second term here. We record this first term, h of e equals to this. Now for the second term, h of x given ey. It's an interesting term. So first, this is conditioning on e, so we will divide into two parts. Probability that e equal to 0. So if e is equal to 0, then x equal to gy. Therefore, under e equal to 0, if you know y, then you also know x. This is g of y. This is 0. There is no randomness left in x under e equal to 0. Under e equal to 1, so e is equal to 1, you know that x cannot be equal to gy. If x was binary, actually, you will again know x and this will again be 0. But even when x is not binary, it reduces the value of x to just cardinality of x minus 1 values, because it cannot be this value, but it can be any other value. And therefore, since we have a bound on the cardinality of the set in which x takes value, the maximum entropy that you can get here in that case is log of cardinality of x minus 1. Okay, so yeah, so this is basically once again we are writing it as h of x given e equal to 0 y into this probability E equal to 0, probability E equal to 0, and then h of x given E equal to 1 given y, probability E equal to 1. This is sort of bad notation. I have condition on an event and then I have a conditional entropy going on, but I hope you understand what I mean. So this guy only can take x minus 1 values, and therefore you have just this. Okay, so combining this guy, this bound, and this expression with this bound, what we have obtained is that h of x given y is less than equal to binary entropy of probability x not equal to gy plus, again, what's the probability E equal to 1? That's the same thing. Probability x not equal to gy times log of cardinality of x minus 1. Okay, so that's, in fact, that's the bound we were looking for. Okay, so this is my second version here. The conditional entropy is no more than probability of x not equal to y. Okay, so in conclusion, we have now seen two different versions of Fanos inequality. Both are actually pretty important. I just use those two versions as an excuse to give two different proofs, and I suggest that you remember both of them. Actually, they are similar, but their use cases can be very different. So one form is an upper bound on conditional entropy in terms of probability of error, and the alphabet size plays a role there. Alphabet size plays a role here. The other one is again a lower bound on probability of error in terms of mutual information, but this one only applies for a uniformly distributed M. Okay, so that's what I wanted to say about Fanos inequality. Remember it for the next class. See you in the next video.